there will be also quiz. Okay. Now the circle coordinates. Actually, this is essentially just polar coordinates. Okay. Most problems we are doing here can first set up iterative integrals, use polar coordinates to evaluate, okay, to bypass the integral coordinates. Let me give you some ideas what means cylindrical coordinates. It is here's a picture. Okay, so you have a domain which is similar to the city, portion of the city. Okay, so this is a domain region, maybe we call it region. Okay, portion of the city. Not necessarily x. Yeah, in around the z-axis, to be around the x-axis. Okay. Okay. Now we have so every point inside the cylinder will be using using the following coordinate x, y, z, right? So this is this angle theta, and yeah, this distance r. Then you have x equals r cosine theta, y equals r sine theta. You know, it's familiar with polar coordinates for z. Okay? So it's possible um, you have this is r, this is theta, this is z. It's possible a rectangle box, okay, send it to the cylinder. Okay, you know, a rectangle is sent it to a circle, right? And then by this transformation, then now it's a box is sent it to the cylinder. So if this is a region R, this is a region R prime. Okay. And now if you have a portion of the cylinder, then you may have a portion of this box. Okay. But it's not circular, so it's easy to evaluate a triple integral. So if you have a triple integral here, and this is going to be f, y, okay, and then you can change it to the triple integral over here. Now, the only difference here is going to be this are cosine sine theta, right? Now the question is what is this part? Okay, this part is actually just only after b. Let me use a part. Okay, so dv usually is a iterative integral dx by dz, and this dv dx and dr is theta dz. Okay, it's a new variable. So that's addition r from. Yeah, this coming from actually this coming from the so-called Jacobian. Okay? And we here, you know, you start an even more general transformation. So what we have here is what is how do we get this out here? Okay? So in general, PV is going to be the determinant of this matrix x, y, z, and here r theta z, x, and the dv prime. X. And what is this? Let me show you the details. This is going to be x, and then dx is partial derivative y with respect to theta, and then partial derivative with respect to z. Okay? And as a matrix, you will see that is going to be here r is the cosine theta. This is sine theta. Here's 0 because z equals z when differential with respect to 0. And here is going to be differential with theta, so r sine theta dv times dr theta represents. Okay, so this is where the start. Then we can study evaluate superintegrals over the cylinder. Okay, and then maybe a portion of the cylinder. Okay, we can also, like I said, cast the cylinder coordinates, okay, to 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 solve the superintegral. Okay, let's take a look at examples. Okay, here's the first example, number 18, number 18 here. Okay. So this is where the superintegral is increased by z x squared and z equals 4. Okay. So this is not cylinder. Okay, the solid is not cylinder, it's a portion of the cylinder. Okay. So first one, let's draw the okay. Z equals xy plus y squared. So this is the surface. And here z equals okay, so it's plane, right? So this is a solid inside. Okay. Now it's portion of the cylinder. Why? Because when you extend it, right? This is just a portion of the cylinder. Okay. So let's draw let's color this solid. It's gonna be inside like this. Okay. So this is a portion of the cylinder. Now, how do we set up an integral? How do we simplify this? Well, you can do as follows. You take opposite point inside x, y, you take a point inside the solid, right? And you express it like that's up cos theta equals sine theta. Z equals
Professor,
yes.
Professor, for some reason we can't hear properly.
Oh,
You sound like very far away and like
yeah, that's probably I did not use another computer here. So let me
I cannot hear what you just said.
okay. Let me switch to let me use hold on. Yeah, let me use my Zoom. Yeah, I need a sorry. I need to use another computer microphone. Otherwise, it's probably right. This is just a second. Okay. Let me let me continue this, but I have to switch to the other one. Okay, in a minute. Okay. So this is yeah. This what I usually do is today I do not start the other computer with some problem. I'm going to restart the other computer so I can use log in as another person. I can use the microphone for that. Okay. So this is my internal microphone, my tablet PC. Not working very well. All right. So this is yeah. If I can just a second. Okay. Yeah, that works. Now you can you hear me now?
Yes.
Yes, much better.
Okay, great. So let's use this. Okay, so now we use a so-called cylindrical coordinates. Essentially, it's polar coordinates, and this is the inside the cylinder. Here's a D. Okay, this is a domain D. Okay, so this is a cylinder, and it's a sense. Okay, if it's complete cylinder, then you get the box, right? This is R, this is theta, this is a Z. Okay. Now we see that the point for the fixed R and the theta, or for the fixed X and Y. Okay. For each X and Y, or R and theta corresponding. Okay, R and theta. This Z, okay, on this vertical line. Okay, the Z has a lower bound and upper bound is 4. Okay, lower bound is just x squared plus y squared. Now x squared plus y squared can be also written as r squared. Okay, so that means we consider those points, and actually over here I have a portion of the rectangular box, but it's good, it's a rectangular box. Okay, it's under this roof, the region. No, above the roof. Okay, not under the. Okay, so this portion. Okay, so this is centered to this is R prime. Okay, so now you can translate the triple integral, which is the integral of Z, right, to a triple integral of R prime. Okay, this is R prime. Okay, and that is R. Okay, and then still Z is still Z. No, not changed. Okay, and then this will be R dV prime. Okay. Now, because this region is much better, okay, and it is over the domain D prime, okay, D prime is going to be from 0 to, let's see, we have to find out. Okay, I is what is the upper bound for the R? Okay, because x squared. This over here, you see the intersection. So I think this I is going to be, here's x squared plus y squared is less than 4. Okay, less than 4. So I is going to be less than 2. And this is from 0 and 2 pi. Okay, so we fix that. And this will be, how do we evaluate this triple integral over this a portion of the rectangular box? And use a double integral d prime, okay? And then that's a dA, okay? And then, and for each, okay, I just said that for each point in this disk, in this rectangle, the z variable changes from r squared to 4, okay? So that is the z, and r and the d z. Okay, we already mentioned that on the top. Okay, so first you evaluate this. You get half of z square r. Evaluate, okay, at the two endpoints. So you will get half of 4 square, right? And minus r to the fourth power. Okay. Yeah, r squared, r to the fourth power. Then you evaluate over the rectangular box. Okay, which doesn't matter which one first. It's going to be r is going to be from 0 to 4. Yeah, let me check. R is 0 to 4. Okay, and the theta is from 0 to 2 pi dr d theta. Okay, okay, and if the theta is inside the d theta dr. Okay,
0
then
to
you
4.
evaluate
0 to 4.
Yeah, this is you see z is between r squared and 4. We already mentioned that at the very beginning, right? Z is between r squared and 4. Okay, so
yeah, you have it 0 and 2 for the first one.
0 and yeah,
Okay.
0 and 2, yeah.
Okay.
I is between 0 and 2. So this d prime is the disk here. It's bottom here, this disk. Okay.
All right.
So it's a 2 here and a 2 pi. Okay. So that's why it's between 0 and 2. Then you evaluate this integral with respect to z, right? And half of z squared, then you plug 4 for z, plug r squared for z. Okay. Then anyway, it's independent of theta. So inside you get 2 pi over 2. Let's take this out. And here, and the 16r minus r to the fifth dr. Okay. Then you find the antiderivative of this. It's 8r squared minus 1 over 6r to the fifth to the sixth. Okay. Then you plug 2. Okay. Then you solve the problem. Okay. So after you simplify, you get an answer. All right, but I just said that you don't need to use a cylindrical coordinates to solve this problem. I'm just go back and essentially what they're doing here. Yeah, this is just use the iterated integral. Then when you come to the double integral, you use the polar coordinates. So there's nothing new here for the cylindrical coordinates if you know how to use iterated integrals to evaluate the triple integral. Okay, let's go back to the problem again, and this is this is a 4 here, right? This is and the z equals x squared plus y squared. Okay. And this is a triple integral. Yeah, that use I'm sorry, I'm confused. Use I and E doesn't matter. Okay, let's use the E in the book. That's okay. So now, I prefigured that. Okay, change to that. So how do you set up this triple integral to set up an iterated integral for this triple integral? So what I'm trying to do here is I project this to a disk D. Okay, D is going to be x and y, x squared plus y squared less than equal to, I think, 4. Okay, yeah. When z equals 4, and then the up circle, the horizontal circle on the top is x squared plus y squared equals 4. Okay. All right. So now I'm going to
yeah, I'm going to set up the iterative integral. So for each point x and y in this D, okay, z variable on those vertical lines, we can, yeah, this solid occupied by those vertical lines. So you needed to xy fix, but you needed to know the upper bound for the z, a lower bound for z. So it's x squared plus y squared less than or equal to 4. Okay. So then this triple integral becomes a double integral, and z is from x squared plus y squared to 4, and z and the dz and the dA. Okay. Then let's finish this inside. Yeah, evaluate the integral inside. So half of the square. Okay. Then you get half of 4 square minus x squared plus y squared and square and the dA. Now you get a double integral over the circle, which is the circle was radius 2. Okay, here's 2, here's 2. That's my D. Okay. Then you can, of course, you use the polar coordinates, you know, so, and x equals r cosine theta, y equals r sine theta. Okay. And the I is between 0 and 2, theta is between 0 and 2 pi. And finally, I got from 0 to 2, from 0 to 2 pi, half of 4 squared minus r squared and square. And you get, here's dr, don't forget the theta dr. So you end up with the same integral at the end. So it's going to be inside 2 pi over 2. Okay, and then you get what we get. Okay, so I stop here. You know, you can find the antiderivative. Well, let me finish that. Okay, so find the antiderivative. 16. This will be 16. R and R to the 5th. You will get 8R squared minus 1 over 6 R to the 6th. Okay. All right, so let's finish it up. All right. So now let's take a look at another problem, number 20. Okay. Evaluate this triple integral. Here's x minus y dv. Okay. I is the solid that lies between two cylinders. One, between the cylinder x squared plus y squared equals 1 and x squared plus y squared equals 16. And also above the xy plane, and wow, that's too complicated. And below the plane z x equals y plus or z equals z equals y plus 4. Okay, so it's pretty challenging. It's pretty challenging to draw the picture, but at least we can draw the two cylinders. Okay, so this is a cylinder, right? The cylinder inside is a unit. This outside is going to be something like that. Okay, so the two cylinders. Now, XY plane is easy, just XY plane, right? It's at the bottom. How can I draw Z equals Y plus 4? Z equals Y plus 4 is in the YZ plane. This should be a strict line with slope 1 and passing through that point. So what you get to imagine is a line, okay, and a familiar line. So you get a plane. Now it's harder to draw the plane, but I think you just the plane, which is going to be no restriction on X. Okay, so how can I draw the plane? It's harder to draw. Okay, anyway, it cuts through the through the yeah, it cuts through the yeah, it's cuts through the solid. Something like that, okay? So that's okay. Okay. We just sketch the graph, right? And you use a plane. This plane will be yes. Yeah, let's keep it the picture. Okay, it's not perfect. Okay, so that means, okay, now you can use a polar coordinate. Okay, that's domain I call the D. That's a D. So D in the XY plane. Okay, so this is going to be x squared plus y squared is less than 16 and greater than 1. Okay, so it consists of yeah, it's between two circles. Okay, and then for each point x and y in the D. Okay, for each point x, y in the D, we have we just look at, yeah, take arbitrary point. So x, y, z, and the solid that consists of all those vertical lines. Okay, so those are the vertical lines in the solid. I want to, so if x, y are fixed, right? I want to see what is the upper bound for z and the lower bound for z. So z is clearly above, the point is above the xy plane, so z is greater than or equal to 0, but less than y plus 4. Okay, because it's the upper bound is controlled by the plane, cuts through the solid. Okay, that's it. Then very similar to the last problem, this triple integral E, yeah, let's use R here. Okay, R and x minus y, right? And the dv can be evaluated using this iterated integral. The first part is a double integral. The second part is from z 0 plus 0 to y plus 4, and that is going to be, yeah, x minus y dz and the dA. Okay, so first of all, you evaluate this single integral inside, and it's independent of z. So you will get x minus y, evaluate at the two endpoints, right? Then that is with respect to z. So x minus y, y plus 4, and the dA. Now you end up with integral on a disk, right? on 2 disks. Okay, so now what is a D? So the little circle and odd circle. So that is a D. Okay, so the D is going to be this portion. Okay. I'm surprised only 10 students here, so they just come here to take a quiz. All right, so that is going to be, you multiply this up, it'll be x times y, y minus y. Okay, 4x minus 4y, and dA. So definitely you have to use a polar coordinates, okay? Polar coordinate x equals r cosine theta, y equals r sine theta. Now here's r is clearly is between 1 and 4, because I think the other one is x squared plus y squared equals 16. This one x squared plus y squared equals 1. So 16 is 4 squared. So the radius is going to be between 1 and 4. Theta, no restriction, it's between 0 and 2 pi. So what you get here is from 1 to 4, from 0 to 2 pi, okay? And r, x times y is r squared cosine theta sine theta minus r squared sine squared theta, okay? And plus 4r cosine theta minus 4r sine theta, okay? And r d theta dr, okay? Now, when you evaluate these integrals with respect to theta, because this is integral over from 0 to 2 pi, so all of them will be 0 except for the one in the middle. You know why? Yeah, so this integral, when you this integral of this will be 0 over from 0 to 2 pi, because positive negative will be canceled out. Okay, this is half of sine 2 theta. When you find the antiderivative, it's going to be 0. So what is left is only this part. Okay, the rest of them already gone. Okay, I just needed to focus on this one. Okay, then to find this, it's going to be, I think it's a double angle, right? Cosine 2 theta equals 1 minus sine square theta. You solve for sine square theta, you will get 1 minus cosine 2 theta, okay? D theta, dr, okay? And cosine 2 theta, if we evaluate the integral from 0 to 2 pi, it's also 0. So what I got here is negative r cubed over 2 and times 2 pi, okay? Dr, okay? So this will be negative pi r cubed dr. Then you find the antiderivative of that function, r to the 4th power, divided by 4, evaluate at the 3 endpoints. And there is a negative sign in front of that, don't forget. So it's negative pi over 4, 4 to the 4th power, okay? So I simplify a little bit, 4 cubed pi. Okay. So I did not use the cylindrical coordinates. I just said that that's not necessary if you know how to set up iterative integrals to evaluate the triple integrals. The iterative integrals, the second step, it involves cylindrical coordinates. Sorry, it's my mistakes here. It's from, that was a small mistake. I need to put 1 here instead of yeah, let me erase this part. Okay, it's from 1 to 4, not from 0 to 4. Okay. Yeah, from 1 to 4. Okay, so it's negative pi over 4 and 4 to the 4th power minus 1 to the 4th power. Yeah, that is answer. Okay. Be careful. All right, let's do step by step. You know, I try to do all these other number problems, even number problems. Okay. So find the volume of the solid. Okay. That lines within both the cylinder x squared plus y squared equals 1 and the sphere x squared plus y squared plus z squared equals 2 squared. So the sphere has a radius 2. Okay. So draw the picture, right? Step 1. Okay. Draw the picture. Step 1. So you have a cylinder. You have a sphere. Sphere has a radius 1. So the cylinder will be inside. Okay. Cylinder is smaller, right? But it will go through the sphere. So you guys cut here. Cut here. We want to find out the volume of this portion of the cylinder, but it's not flat. Okay, it's not on the top part and bottom part. They're both not flat. That's just portion of the sphere. So how do you solve this problem? You can remember you can find the volume of the small cap and multiply by 2 because that's another one at the bottom, and then plus the volume of cylinder. That's okay. But you can do it one step. Okay, what I'm trying to do here, we are going to just directly use the cylindrical coordinates. That's fine, right? So for the cylindrical coordinates, an arbitrary point inside this solid x, y, z, and you write down the coordinates. Okay, z equals z. Then you should realize that x squared plus y squared is smaller than or equal to 1, right? X squared plus y squared smaller than or equal implies r is less than 1, right? Okay, clear. No restriction on the theta. Okay, no restriction on the theta. Okay, so theta is between 0 and 2 pi. Okay, now for each I and theta, okay, or x and y, what is the lower bound for the z and what is the upper bound for the z? Okay, you draw the vertical line. You find out the z is determined by the sphere. Okay, z is determined by sphere. The upper bound, when you solve the equation for the sphere, is going to be 2 squared minus x squared y squared, right? And they are negative 2 squared minus x squared minus y square root of x squared minus y. So this is the same as if you use a cylindrical coordinates, you can change it to this. Okay. Okay. So so what we're doing here is we trying to let me draw the original. I'm trying to draw the region in this r theta coordinate system. Okay? R is no restriction on r, so r is 1 from 0 to 1, and that is here's from 0 to 2 pi. But for each I and the theta, the z actually changes, right? Z equals square root of its portion of the circle. Okay, I think it's circle like that. Okay, yeah, this is a 2. Okay, this is a 2. Okay, when I equals 1, I get square of 3 is equal. Yeah, so the bottom part is like that. Okay, so what I got here is it's harder to okay. Yeah, my drawing here is wrong. Okay, I need a okay. So how can I draw the bottom part? So the bottom part is looks like that. Okay. Yeah. Yeah. It's a 3D. So anyway, it's a symmetric. I'm not gonna draw this part here. It's a symmetric. Okay. So this is okay, it's a surface. Okay, it's a surface. Anyway. So this is yeah, let's stop here. Yeah. So this is a solid, okay, but it's better. It's over the rectangle. Okay, this is my E prime. Okay, all right. So this should be integral over E. Okay, and the volume, right, is just the integral of the constant function 1. Okay, and this is going to be the triple integral over E prime, and then here's R and the dv prime. Okay, so it becomes an integral over this. Now this E prime, okay, you still have to change it to the iterated integral, right? So the D prime is going to be I and the theta. I is between 1 and 0, and the theta is between 0 and the 2 pi. Okay, so it will become the triple integral, double integral D. Okay, and this is Z is between this 2 and R and the dz and dA prime. Okay, dA prime is dr d theta. Okay. So here we use just cylindrical coordinates, but still you still have to evaluate is a double iterated integral, and this double integral is not over the circle already. It's already in the over the rectangle. Okay, so let's evaluate this inside first. R is a constant, so it's just 2R. This 2 square minus R square dA prime. Then yeah, it's double, okay, right? Then this becomes 0 to 2 pi, and from 0 to 1, 2R 2 square minus R square dr d theta. Then you have to use a substitution. But anyway, it's 2 pi is constant, right? So I put a 2 pi here. Don't worry about this. So let's focus on this integral. Then use the substitution. Okay, you let u to be 2 square minus R square. Du equals negative 2R dr. Okay, so the integral. Okay. When I equals 0, I get 4. When I equals 1, 4 minus 1 is 3. And then 2RdR is going to be negative du, so it's a u to the 1/2 negative du, okay? Yeah, so you can, if you switch the order, okay. So now we find the antiderivative is 2/3 u to the 3/2. Okay, and then 2 times 2 is 4 pi. Here's 4 3/2 minus 3 to the 3/2. You don't need to simplify. This is already, I think it's a simplified version. Okay, a little bit simplification will be 4 to the 1/2 is 2, so it's 8. And this will be 3 squared 3, you know, that's okay. So this is answer, yeah. And we apply the so-called cylindrical coordinates directly, okay? A so-called cylindrical coordinates just like a transformation, yeah, from one region to another region, okay? So the pre-image is better than the current image. So you can easily set up the iterated integrals. Okay, that's so my opinion. If you know how to set up iterated integrals, you don't even mention cylindrical coordinates. Okay, you just use the polar coordinates later when you after you set up the iterated integrals. Okay. Okay. Let me just do one more problem. Some problem now going to evaluate, and I will just set up integrals. Okay, so this is a problem 30, which is slightly different from that. You're already given the iterated integral. So evaluate the integral by changing to cylindrical coordinates. So you already have the iterated integral. Okay, this is a problem from -3 to +3. Oh, that's dx. Okay, so we have to, this is a final version of the iterated integral for some triple integral. So very first step, you have to express it as a triple integral over x squared plus y squared and the dv. So the question is, what is E? Okay, so how do we understand this? Okay, so take a look at the picture over there. So x is all side, x is no restriction. So for each x between -3 and +3, okay, the y variable is between 0 and y satisfied or controlled by. Okay, then for the fixed y, okay, then z satisfying z between 0 and 9 minus x squared and x squared. Okay. Okay. All right. So at least we can combine those two on the top. X is between -3 and positive 3. Y is between 0 and 9, right? So x axis, y axis, right? Between 0 and square root 9 minus x squared. So what you get actually here is a circle. So this is my D. Okay. So this above describes the domain D. Okay. Describe the domain D. Okay. Then for each point in this D, right? And the Z is between 0 and 9 minus x squared minus y squared. So let's look at the equation Z equals 9 minus x squared minus y squared. This is yeah, let's draw the picture now in 3D. Okay. X squared. So x squared plus y squared is it's a semicircle, right? So yeah, this is a D, it's a semicircle. Here's going to be 3, that's going to be -3. Okay, it's a semicircle. Okay. And our Z, the graph of Z equals 9 minus x squared minus y squared, start from 9. Okay. It's a paraboloid going down. Actually, when x squared plus y squared equals 9, Z is going to be 0. So what they got here is a half of this paraboloid. Okay. So that is you know, for every point here, x and y, you draw a vertical line. You draw the vertical lines, and that's the upper limit. Upper limit is determined by the graph Z equals y minus x squared minus y squared. Okay. Okay. So that is a point. All right. So now we get a clear picture of this solid. Okay. Right. Step by step, you get a clear picture. So you can use a polar cylindrical coordinates. Okay, cylindrical coordinates of x equals r cosine theta, y equals r sine theta, z equals z. Okay, so clearly for the semicircle, semi-disk, r is between 0 and 3, theta is between 0 and 0 and pi, but the z, okay, is between 0 and 9 minus r squared. Okay, so this is my E prime. Okay, this is my E prime. Okay, so this triple integral, okay, it's triple integral x squared plus y squared dv is going to be the triple integral over E prime. And here's just r, right? Square root r squared plus y squared is r. But there's addition r here, dv prime. Okay. All right, so now, but still have to go back to the iterated integral because you want how to evaluate the triple integral, right? The triple integral, but the good part is this portion, this is a d prime. This portion is a rectangle, so, okay? And the z is between 0 and 9 minus r squared. Here's r squared, dz, and here dA prime, okay? And I can simply write r squared, 9 minus r squared, because it's constant. Okay, now we are on the semicircle. Not on semicircle, it's actually on a rectangle. Here's a pi. That's 3, right? Yeah, it's going to be 3. All right, so let's do this. And this is a 9r squared, r to the 4th power. So let's do this from 0 to pi. and from 0 to 3, right? Yeah, I'll from 3 to 3. And then the antiderivative will be 3r cubed minus r to the 4th. Okay. No, before, before, yeah, don't do that yet. Yeah, so it's 9r squared minus r to the 4th and the d theta. So I'm not going to finish this. I'm not going to finish this computation. I'm not going to finish this computation because we don't have time right now. Okay, and but it's almost done. Okay, so everybody can evaluate this integral. Okay. All right. So let me send you this. I hope most of the students are here. Okay, let me give me a minute. I have to send it by email first, then I show up the screen. Okay, show up on the screen. Okay, so now I'm going to log into the file Canvas, because send it by group message have to go to the Canvas. Okay, this is a mail. That's okay. So this is sent it to you already now. Let me bring up the quiz on the screen. My file.
Professor, we didn't get it by email yet,
Oh,
nor we can see it on Zoom.
yeah, right now I'm going to show to you, but I think that's already sent out. This is a sharing. Okay, so this is a file. Quiz, yeah, quiz 1, 2, 3. So what? Yeah, quiz 6, problem 1, 2, 3.
Professor?
Hello?
Yeah, what time is this due?
Oh, normally it's 10:30, but I can leave it a few minutes later because I emailed to you a little bit late.
Okay, thank
So
you.